Hello and welcome to Science Night Tales. I'm glad you have found this quiet moment to drift. Tonight, we look upward toward the most familiar object in our night sky, the moon. For as long as humans have looked up, it has been there, silent, constant, a glowing disk, a sliver of silver, a quiet companion to the Earth. But if you watch it carefully, you'll notice something strange. The moon changes its shape as the nights pass, but it never seems to turn. Night after night, year after year, century after century, we see the same face, the same dark plains, the same bright highlands. It appears frozen, locked in place. Why? Why do we never see the other side? Tonight, we will explore the quiet, invisible forces that govern the moon's motion. We will travel back billions of years to a time of violence and fire and trace the slow, patient work of gravity that turned a chaotic, spinning world into the still, synchronized companion we see today. It is a story of balance, of motion hidden within stillness. So, let your mind settle and let's unravel the gentle mystery of the moon's unchanging face. On a quiet night, if you step outside and look up at the sky, you will almost certainly find it, the moon. Sometimes it appears as a thin silver crescent hanging delicately above the horizon. Other nights, it is a glowing half circle, dividing light from shadow with a perfect line. And every few weeks, it rises as a full, luminous disk, bathing the landscape in pale, quiet light. For as long as humans have looked upward, this familiar presence has been there, silent, constant, watching over oceans, mountains, forests, and cities alike. But if you pay attention long enough, you may begin to notice something strange about it. The moon changes its phase, but it never seems to turn. Night after night, year after year, century after century, the same shapes appear on its surface, the same dark plains, the same pale highlands, the same familiar patterns of craters. Some people imagine they see a face in those shadows. Others see a rabbit or a figure carrying wood. Different cultures have given those patterns many meanings. But regardless of what we see in them, the shapes themselves remain the same. Every time we look at the moon from Earth, we are looking at the same side. The same hemisphere that humans have gazed upon for thousands of years. No matter where you are on Earth, no matter when you look, the moon always seems to present the same unchanging face. And that raises a quiet but fascinating question. Why? Why does the moon never turn? Why don't we ever see the other side? After all, nearly everything in the universe rotates. Planets spin, stars rotate, galaxies slowly turn through space. Even the Earth beneath our feet completes a full rotation every 24 hours. Rotation seems to be a universal rule. So why would the moon be any different? Why would it remain perfectly still in the sky as if frozen in place? For most of human history, no one knew the answer. People simply accepted the moon's steady appearance as one of the quiet certainties of the night sky. Only in the last few centuries did scientists begin to carefully measure the moon's motion and realize something subtle was happening. Because the moon is not actually motionless, not at all. In fact, the moon is rotating, right now, at this very moment. Slowly, quietly, continuously. The moon is turning in space just like the Earth. Yet somehow, despite that motion, the same side of it always faces us. At first glance, that sounds impossible. If the moon is spinning, then over time we should see every side of it. The far side should gradually rotate into view. Craters we have never seen before should slowly drift across the lunar surface. But they never do. Instead, the same familiar face remains pointed toward Earth with remarkable consistency. The explanation for this strange behavior lies in something subtle and beautiful. The moon is rotating at exactly the same rate that it orbits the Earth. In other words, it takes the moon about 27.3 days to travel once around our planet. And it also takes the moon about 27.3 days to rotate once on its own axis. Those two motions, rotation and orbit, are perfectly synchronized. This means that as the moon travels around Earth, it turns just enough to keep the same hemisphere facing us the entire time. Imagine holding a ball in your hand while you walk in a circle around a friend. If you always keep the same side of the ball facing them, you must slowly rotate the ball as you move. By the time you complete the circle, the ball has turned exactly once. To your friend, however, the ball never seemed to rotate at all. The same side always faced them. That is essentially what the moon is doing as it moves through space. It is turning once for every orbit around Earth. And because those two motions match perfectly, we never see the far side. From our perspective, the moon appears calm and unmoving, a silent disk suspended in the darkness. But this stillness is not the absence of motion. It is something far more delicate. It is motion in perfect balance. Every step of the moon's orbit is matched by a tiny turn of its rotation. Every day of its journey is accompanied by a slow and precise adjustment of its orientation. The result is a remarkable illusion, an object that is spinning, yet appears completely still. Tonight, if you step outside and look up again, the moon may seem peaceful and unchanging. Perhaps it hangs above the rooftops of your city, glowing softly between drifting clouds. Or perhaps it rises above distant hills, illuminating the quiet landscape below. Stars slowly slide behind it as the Earth turns through the night. The moon itself glides gently across the sky, and yet its face remains the same. The same ancient craters, the same broad grey plains formed billions of years ago. The same patterns that sailors once used to navigate oceans and poets used to inspire stories. It feels almost as though the moon has chosen to look at Earth forever, as though it has fixed its gaze upon our world. But this alignment is not the result of intention or chance. It is the outcome of a long and intricate relationship between two celestial bodies, a relationship governed by gravity. Because the Earth does not simply pull the moon toward it, its gravity also stretches the moon ever so slightly. Invisible forces tug at the lunar surface, creating subtle distortions deep inside the rock. Over immense spans of time, those forces changed the moon's motion. They gradually slowed its rotation until it matched its orbit perfectly. This process took millions upon millions of years. Long before humans existed, long before life on Earth looked anything like it does today. Yet the result of that ancient process is something we can observe every night. The quiet stillness of the moon's familiar face. But the story behind that stillness is far from simple, because the moon was not always like this. Long ago, shortly after its formation,
the moon was spinning much faster. Its surface was hotter, its orbit was closer to Earth, and its appearance in the sky would have been dramatically different from the calm presence we see today. Over billions of years, powerful yet invisible forces gradually reshaped the entire Earth-Moon system. They slowed the moon's spin. They pushed the moon farther away from our planet, and eventually they created the delicate gravitational balance we see now. What appears tonight as a motionless disk in the sky is actually the result of an ancient cosmic negotiation, a slow conversation between Earth and Moon, written in gravity, a conversation that unfolded over billions of years. Even today, that conversation has not completely ended. The Moon continues to drift slowly away from Earth by about 4 centimeters every year.
Earth's own rotation is gradually slowing as well. The tides that rise and fall across our oceans are part of the same ongoing exchange of energy. In other words, the Earth-Moon system is still evolving, still adjusting, still quietly shaping the future of both worlds. But the most remarkable part of this story may be how gentle it appears from our perspective. Because from here on Earth, the Moon simply looks calm, a steady companion in the night sky, unchanging, silent, familiar. And yet, beneath that calm appearance lies one of the most elegant balances in our solar system. A world that rotates while appearing perfectly still. A motion so precisely matched to its orbit that the illusion has endured for billions of years. So, the next time you see the moon rising into the evening sky, you might pause for a moment and consider what you are really looking at. Not a frozen object suspended above us, but a world that is slowly turning through space. A world whose motion has been sculpted by gravity into perfect synchrony. And that raises an even deeper question. How did gravity manage to achieve such an extraordinary alignment? How could invisible forces stretch a distant world, slow its rotation, and guide it into this delicate balance? The answer lies in processes that unfold almost too slowly for the human mind to imagine. Forces that operate quietly across millions and billions of years. Forces that can reshape entire planetary systems without ever being seen. To understand them, we must look beyond the simple image of a still moon in the night sky. We must look deeper into the hidden mechanics of gravity itself. And once we do, the familiar face of the moon begins to reveal a much larger story. A story of stretching worlds, of friction hidden inside solid rock, of ancient tides raised not in oceans, but in the very shape of a moon, and of a cosmic dance between Earth and Moon that continues even now with perfect patience. Because what seems like stillness in the sky is actually the result of motion so precise and so enduring that it has become almost invisible. In the next part of this journey, we will begin to uncover how that delicate balance formed, step by step, force by force, until the mystery of the moon's unchanging face becomes something even more fascinating. A quiet demonstration of how gravity can shape the motion of entire worlds. On another calm night, you step outside and look up again. The moon is there, as it has always been. Perhaps it hangs low over the horizon, glowing faintly through the haze of the atmosphere. Or perhaps it sits high above the dark landscape, surrounded by scattered stars. Either way, Its appearance feels familiar in a way that few other celestial objects do. The same dark plains stretch across its surface. The same pale highlands frame its edges. The same ancient craters scatter across its face like frozen footprints from a distant past. Night after night, those features remain exactly where we expect them to be. A large dark basin called Mare Imbrium rests near the upper left portion of the lunar disk. The bright ray system of the crater Tycho spreads outward like delicate scratches across the lower half of the moon, and the long chains of mountains and ridges hold their positions like silent landmarks. These features do not drift across the surface. They do not slowly rotate out of sight. Instead, they remain fixed in place, so consistent that astronomers have been mapping them for centuries. Someone living 1,000 years ago could look at the moon and recognize the same patterns that we see today. From our perspective on Earth, the moon appears almost perfectly steady. And yet, at the same time, we know something else must be happening, because the moon does not stay in one place in the sky. Each night, it shifts slightly eastward among the stars. Over the course of about a month, it completes a wide arc around our planet, returning again to roughly the same position relative to the Sun and Earth. In other words, the moon is clearly orbiting Earth. And any object that travels around another body in space must be moving. It must be turning. So the question becomes more precise now. If the moon is orbiting Earth, why do we still see the same face? The answer lies in a remarkable numerical coincidence, or rather, what seems like a coincidence at first glance. The moon takes about 27.3 days to complete one full orbit around Earth. Astronomers call this the sidereal orbital period, the time it takes the moon to circle our planet once relative to the distant stars. But something equally important is happening at the same time. The moon also takes 27.3 days to complete one full rotation on its own axis. Its spin period and its orbital period are identical. That simple equality changes everything, because when those two motions match perfectly, something unusual happens. Imagine the moon at the beginning of its orbit. At that moment, one particular hemisphere faces Earth. Now, as the moon begins moving along its path around our planet, it also begins rotating slowly. Day after day, it advances along its orbit, and day after day, it turns a little bit more. But the key is that it rotates at exactly the same pace as its journey around Earth. By the time the moon has traveled halfway around its orbit, about 2 weeks, it has also rotated halfway around its axis. And by the time it completes the entire orbit, it has rotated exactly once. One orbit, one rotation. Perfect synchronization. The result of this coordination is subtle but profound. At every moment during its journey, the same hemisphere of the moon continues to face Earth. As it moves forward along its orbit, its slow rotation constantly adjusts its orientation, just enough to keep the same side pointed toward us. From our perspective, nothing seems to change, but in reality, the moon is quietly turning the entire time.
A helpful way to imagine this is through a simple movement here on Earth. Imagine standing face to face with a friend. Now, begin walking in a wide circle around them. If you want to keep facing them the entire time, you must slowly turn your body as you walk. Your feet trace a circular path, but your gaze remains fixed on your friend. By the time you complete the circle, you have rotated once. Yet, from your friend's perspective, you never turned away. The Moon is doing something very similar. As it travels around Earth, it rotates just enough to keep the same hemisphere directed toward us. The motion is continuous, smooth, and perfectly balanced. And because this balance has remained stable for billions of years, the illusion of stillness is extraordinarily convincing. Tonight, if you watch the Moon for several hours, you will notice it gliding slowly across the sky. That movement, however, is not caused by the Moon itself. It is mostly the result of Earth's rotation, carrying the sky overhead as our planet spins beneath us. Against the background of distant stars, the Moon drifts gradually eastward each night. Yet the face it presents never changes. The same craters remain in view. The same shadows carve out the same familiar shapes along the boundary between day and night on the lunar surface. Even as the Moon moves through space at thousands of kilometers per hour, its orientation toward Earth remains nearly constant. The effect is almost hypnotic. A world in motion that appears calm and unchanging. Astronomers have a name for this special relationship between rotation and orbit. They call it tidal locking. Tidal locking occurs when a celestial body's rotation period becomes equal to its orbital period around another object. When that happens, one hemisphere of the smaller body always faces the larger one. In the case of the Earth-Moon system, the Moon is the locked partner. One side of the Moon forever faces Earth. The other side, often called the far side, remained completely unseen by human eyes until the first spacecraft traveled beyond the Moon in the 20th century. For countless generations before that moment, humanity could only imagine what might exist on that hidden hemisphere. But the key idea is this. The Moon's familiar face is not the result of the Moon being frozen in space. It is the result of a very precise relationship between two kinds of motion: rotation and orbit. Each step of the Moon's journey around Earth is matched by a tiny turn of its axis. Every orbit includes exactly one rotation. Together, those motions create the illusion of perfect stillness. So the face we have always known, the craters we recognize instantly, the patterns people have imagined into animals and figures for thousands of years, are not fixed by chance. They are held in place by a delicate and exact coordination of motion. A coordination that has endured for nearly the entire history of the Earth-Moon system. The Moon does not simply hover above us. It participates in a slow and elegant dance with our planet, a dance whose rhythm is measured in weeks, whose choreography was written billions of years ago, and whose precision is governed entirely by gravity. And yet, this explanation raises a deeper question, because matching two periods so perfectly, rotation and orbit, does not happen automatically. Something must have shaped the Moon's motion. Something must have gradually adjusted its spin until the two became synchronized. How could gravity accomplish such a precise alignment? What forces could slow an entire world until its rotation fell into step with its orbit? The answer lies in processes that are almost impossible to see directly. Processes that unfold quietly inside solid rock. Forces that stretch worlds ever so slightly and dissipate energy over immense spans of time. So the face we have always known is not frozen by chance. It is held, gently, precisely,
in place.
But how does gravity achieve such perfect alignment? The answer lies in forces we cannot see. Forces that have been acting patiently for billions of years. To understand how the Moon reached this delicate balance, we have to look at a force that is always present but almost never visible: gravity. We often imagine gravity as a simple pull between two objects. Earth pulls the Moon toward it, keeping the Moon in orbit. The Moon pulls back on Earth, raising the tides in our oceans. But gravity does something more subtle as well. It stretches things. Any object in a gravitational field experiences slightly different forces across its surface. The side closest to the source of gravity feels a slightly stronger pull than the side farther away. For something rigid and massive like the Moon, the difference is small, but it is not zero. Earth's gravity gently stretches the Moon along the line connecting the two worlds. The result is a pair of tiny distortions called tidal bulges. One bulge forms on the side of the Moon facing Earth, where gravity pulls most strongly. Another forms on the opposite side, where the Moon's inertia slightly resists Earth's pull. These bulges are extremely small compared to the Moon's overall size. The lunar surface is not dramatically deformed. To an observer standing there, the shape would appear almost perfectly spherical. But on a planetary scale, even tiny distortions matter. Because once the Moon develops these bulges, gravity begins to interact with them. If the Moon were already rotating at exactly the same speed as its orbit, the situation would be simple. The bulges would remain perfectly aligned with Earth, always pointing directly toward and directly away from our planet. But early in the Moon's history, things were very different. The young Moon was spinning much faster than it does today. Instead of taking 27 days to rotate once, it may have completed a full spin in just a few hours.
That rapid rotation created a problem. As the Moon turned, the tidal bulges created by Earth's gravity could not stay perfectly aligned with the Earth-Moon line. The Moon's rotation carried them slightly ahead. Imagine those bulges like gentle bumps on the lunar surface. As the Moon spins, those bumps move with it. But Earth's gravity continues pulling on them, trying to drag them back into alignment. The result is a small but constant misalignment. The bulges are pulled slightly forward by the Moon's rotation, while gravity tries to pull them backward toward Earth. This tiny offset creates something extremely important: a torque. Torque is a twisting force. It acts like a subtle brake on the Moon's rotation. Earth's gravity pulls backward on the forward shifted bulges, gradually slowing the Moon's spin. The effect is incredibly gentle. No sudden jerks, no violent collisions. Just a steady, persistent resistance applied across millions and billions of years. Inside the Moon, the rock itself plays a crucial role in this process. The Moon is not perfectly rigid. Its interior can flex slightly under stress. As gravity stretches and releases the lunar material again and again, the rock experiences tiny internal movements. These movements create friction deep within the Moon, and friction converts motion into heat. The rotational energy of the Moon, energy that once made it spin rapidly, began to dissipate slowly inside the lunar interior. Not in a dramatic burst, but as an almost unimaginably slow leakage of energy. Scientists estimate that during parts of the Moon's early history, this process may have dissipated energy at rates reaching tens or even hundreds
of gigawatts. That sounds enormous, and on a planetary scale, it is. But spread across the entire mass of the Moon and across immense spans of time, the effect is gradual. Instead of slowing dramatically in a short time, the Moon's rotation slowed little by little.
The equivalent of centimeters per year in rotational change. A barely noticeable difference in any single moment. Yet, over millions of years, those tiny adjustments accumulate. Tonight, when you look up at the Moon, it appears calm and unchanging. A bright disk drifting slowly across the sky. But every second of the Moon's long history carried this quiet braking effect. Every orbit, every rotation, every stretch of gravity between Earth and Moon. Bit by bit, the torque exerted by Earth's gravity reduced the Moon's spin. As the rotation slowed, something interesting began to happen. The misalignment between the tidal bulges and the Earth-Moon line grew smaller. The bulges had less and less tendency to move ahead of Earth, and because the misalignment shrank, the braking torque also weakened. The process gradually approached a natural endpoint, a point where the Moon's rotation would slow just enough that the bulges could remain perfectly aligned with Earth. When that moment arrived, the torque disappeared. The braking force vanished, because once the bulges pointed directly toward and away from Earth, gravity had nothing left to twist. The Moon had reached equilibrium. Its rotation now matched its orbit. One rotation, one revolution, 27.3 days. At that point, the internal friction that had been draining rotational energy effectively stopped. There was no longer any lag for gravity to pull against. The Moon had entered the stable configuration we observe today. From that moment forward, the same hemisphere remained directed toward Earth. The far side rotated permanently out of view, and the illusion of stillness was born. But it is important to remember that this stillness was not instantaneous. The Moon did not suddenly snap into this orientation. Instead, it was guided there slowly, patiently, through the quiet action of gravity stretching rock, generating friction, and dissipating energy over unimaginable spans of time. Tonight, the Moon appears serene. It hangs above the horizon exactly as it did yesterday, exactly as it did centuries ago. Yet hidden within that calm appearance is the memory of a long transformation. A transformation shaped not by dramatic events, but by gentle forces acting without pause for billions of years. Gravity never grows tired. It never rushes. It simply continues applying the same small influences over and over again until even the motion of a world can change. And so, the Moon's rotation gradually slowed, step by step, until it fell perfectly into rhythm with its orbit. This slowing was not sudden. It unfolded across eons, a conversation written in gravity between two worlds. But to truly understand that conversation, we must go even further back to a time when the Moon itself had only just formed, back to an era when it spun far faster than it does today, and when the Earth-Moon system looked nothing like the quiet partnership we see in the sky tonight. Around 4.5 billion years ago, the early solar system was a far more chaotic place than it is today. Young planets were still forming. Asteroids and planetary fragments wandered through unstable orbits, and collisions between worlds were not rare accidents, but a normal part of planetary growth. At some point during this violent era,
A world roughly the size of Mars, often called Theia, collided with the young Earth. The impact was enormous. Rock was vaporized. Entire regions of Earth's crust were melted. Vast quantities of material were blasted outward into space. For a time, Earth was surrounded by a glowing cloud of debris, fragments of rock, molten droplets, shattered pieces of planetary crust, all circling the planet under the pull of gravity. Slowly, over thousands and then millions of years, those fragments began to gather together. Small pieces collided, merged, and grew larger. Piece by piece, gravity assembled a new world, the Moon. But the newborn Moon looked nothing like the calm object we see in the sky today. It was a world of fire. Much of its surface was covered by a global ocean of molten rock. A vast sea of glowing magma stretched across the young Moon's surface, radiating heat into space. Impacts from leftover debris continued to strike it. The early solar system had not yet become the quiet place we know today, and perhaps most importantly, the young Moon was spinning very rapidly. Instead of taking nearly a month to complete one rotation, the early Moon may have spun once every few hours. Its day was shorter than an afternoon on modern Earth. The Moon was a fast-turning world. At the same time, it orbited much closer to Earth than it does today. Today, the Moon sits about 384,000 kilometers away. But in those early ages, it may have orbited at a distance closer to 20,000 to 30,000 kilometers. From Earth's surface, the Moon would have appeared enormous, perhaps several times larger than the full Moon we see tonight.
Imagine looking up into that ancient sky, a huge glowing moon dominating the darkness, rising quickly, crossing the sky rapidly, setting again within hours. And because the Moon was so close to Earth, Earth's gravity pulled on it far more strongly than it does today. Those tidal forces we discussed earlier, the stretching effect of gravity, were dramatically amplified. The young Moon was constantly being distorted, stretched, compressed, pulled into shape again and again by Earth's powerful gravitational pull. As it spun rapidly, its interior flexed under that stress. The molten layers beneath the surface shifted slowly. The solid rock above them strained and relaxed. Each rotation created internal friction, and friction always converts motion into heat. Inside the Moon, energy from its rapid spin began to leak away, very slowly, very quietly. With every rotation, a tiny amount of the Moon's rotational energy was lost, not in sudden bursts, but in a slow and steady drain. Over hundreds of millions of years, the Moon's spin began to slow, hour by hour, rotation by rotation. The lunar day gradually lengthened, but the energy removed from the Moon's spin did not simply vanish. In physics, energy is conserved. When one kind of motion slows, that energy must appear somewhere else. In the Earth-Moon system, much of that energy was transferred into the Moon's orbit. As the Moon's rotation slowed, its orbit slowly expanded. The Moon began drifting farther away from Earth, centimeter by centimeter, year by year. This outward motion still continues today. Even now, the Moon moves away from Earth at a rate of about 3.8 centimeters each year. But in the early history of the system, the change was more dramatic. Over immense spans of time, the Moon gradually migrated outward, and as it moved away, its rotation continued to slow, from hours to days to weeks. The Moon's spin and its orbit was slowly approaching the delicate balance we see today, a balance between rotation and revolution. If someone could have stood on Earth during those distant ages, the sky would have looked very different. The moon would not have appeared calm and still. Its surface features would have slowly rotated across the disk, craters drifting from one side to the other, dark plains sliding across the lunar face. The moon would have looked alive with motion. But over time, that motion faded. Each million years brought a slightly longer lunar day. Each orbit carried the moon a little farther away. And gradually, the two motions, rotation and orbit, began to synchronize. Eventually, after 3 to 4 billion years, the process reached its natural endpoint. The moon's rotation slowed until it matched its orbital period. One rotation, one orbit, 27.3 days. At that moment, the tidal forces that had been slowing the moon lost their leverage. The tidal bulges could finally remain perfectly aligned with Earth. The braking torque disappeared. The system had reached equilibrium. From that moment forward, the same hemisphere of the moon remained directed toward Earth. The far side rotated permanently out of view, and the illusion of stillness was born. Once this alignment formed, it became self-reinforcing. If any disturbance tried to rotate the moon away from its stable orientation, the tidal bulges would fall slightly out of alignment again. Gravity would reintroduce torque, and the moon would slowly turn back. The system had found its lowest energy configuration, a state of quiet stability. The calm face we see in the sky tonight is the result of that long transformation. Billions of years ago, the moon was a rapidly spinning, molten world orbiting dangerously close to Earth. Today, it is a cool, silent companion drifting through space with perfect patience. Yet, when we look at the moon's surface, we do not see obvious traces of that early, frantic youth. The craters and plains we recognize formed mostly after the moon had already cooled and stabilized. The face we know appears ancient, almost timeless. But beneath that surface lies a deeper memory, a record of a time when the moon rotated swiftly, when its interior churned with heat, when gravity was still shaping the rhythm of its motion. The face we see now carries no memory of that rapid youth on its surface, yet the record remains hidden beneath. And even though the moon is now tidally locked, the story does not end with perfect stillness, because the moon is not completely rigid in its motion. Small movements still occur as it travels around Earth. Subtle motions, gentle oscillations. And because of these tiny shifts, we are able, over time, to glimpse slightly more than half of the moon's surface. Not just 50%, but closer to 60%. If the moon is tidally locked to Earth, it might seem that the story ends there. One face toward us, one face hidden forever. Perfect stillness. And yet, the moon is not completely motionless. If we watch carefully over many nights, something subtle begins to appear. A very small movement, a slow, delicate rocking. Not enough to break the lock, not enough to turn the moon fully toward us, but just enough to reveal a little more than we might expect. Astronomers call this quiet motion libration. The word comes from the Latin librare, meaning to balance or to sway gently. And that is exactly what the moon seems to do. It sways, slowly, almost imperceptibly. At first glance, the moon always shows us the same hemisphere. But because of libration, the view is not perfectly fixed. Over time, the moon seems to nod, then lean, then gently rock from side to side, very slowly, very quietly. And because of this motion, we are able to see slightly more than half of the moon's surface. Not just 50%, but closer to 59%. The hidden side of the moon is still mostly hidden, but its edges occasionally peek into view for a short time. Then they slip away again, like a secret briefly revealed. This gentle motion comes from several different causes, 3 to be exact, each small, each subtle, and each working together to create the moon's slow, graceful oscillation. The first is called libration in longitude. This effect comes from the shape of the moon's orbit. Although we often imagine the moon traveling in a perfect circle around Earth, its path is actually slightly elliptical. Sometimes the moon moves a little faster along its orbit, sometimes a little slower. But the moon's rotation remains steady. It continues turning at the same average rate. And because the orbital speed varies slightly, there are moments when the moon's rotation is a little ahead of its orbital position, and moments when it is a little behind. This causes the moon to appear to rock east and west, back and forth, very gently. From our perspective on Earth, this motion allows us to peek slightly around the eastern and western edges of the moon, just a little. The amount is small, about 7.9 degrees in each direction. The second motion is called libration in latitude. This effect comes from the moon's axial tilt. The moon's axis is tilted slightly relative to the plane of its orbit around Earth. Not dramatically, only by a few degrees. But that small tilt allows us to look slightly over the moon's north pole at times, and slightly under its south pole at others. Over the course of a lunar month, the moon seems to nod slowly, upward, then downward, revealing regions near its polar edges that would otherwise remain hidden. This motion has a range of about 6.7 degrees. The third motion is even subtler. It is called diurnal libration. And unlike the first two, this effect does not come from the moon itself. It comes from Earth's rotation. As Earth spins, observers on its surface move from one side of the planet to the other. When the moon rises, we are viewing it from one position on Earth's surface. Hours later, when it is high in the sky, we are viewing it from a slightly different position. The shift is small, only about the width of Earth's radius compared to the moon's enormous distance. But it is enough to change our viewing angle slightly. Like stepping a few meters to one side while looking at a distant mountain. The mountain does not move, but our perspective changes. This shift lets us glimpse just a little bit around the moon's edge. When all three forms of libration combine, something remarkable happens. Over the course of 27.3 days, the moon performs a slow, gentle dance. A small sway from side to side, a quiet nod up and down, a slight shift from our moving vantage point on Earth. Together, these motions reveal about 9% more of the moon's surface than we would otherwise see. Which means that although the moon is tidally locked and half its surface always faces away from Earth, our view over time expands from 50% to nearly 59%. Amateur astronomers who watch the moon night after night sometimes notice this. A crater near the edge appearing one week, then disappearing the next. A mountain range peeking into view, then retreating again beyond the curve of the lunar horizon. The moon
seems to breathe. Not in the way living things do, but in a slow and patient rhythm of motion, a quiet rocking in space. And yet, despite these gentle oscillations, the fundamental alignment never breaks. The same hemisphere still faces Earth. Gravity still holds the Moon in its long-established balance. The librations are simply the natural result of orbital geometry. Small variations, tiny shifts, not powerful enough to undo billions of years of gravitational harmony. So the Moon remains what it has been for most of its history, a world turning once for every orbit, a companion locked in perfect coordination with Earth. And yet, even within that coordination, there is movement.
A soft sway, a patient rocking, just enough to show us a fraction more of itself. So even in its synchrony, the Moon breathes, just enough to reveal a little more of a world that otherwise keeps its far side hidden. And this breathing is not the only change still taking place, because the Earth and the Moon are not frozen in time. Their relationship continues to evolve, slowly, quietly, year by year. And the next part of our journey will explore that deeper evolution, the gradual transformation of the Earth-Moon system itself. A change so slow that it unfolds over millions and billions of years, yet one that is still happening, even tonight. When we look up at the Moon tonight, it feels timeless. The same familiar craters, the same pale plains, the same calm face that has watched over countless generations. It is easy to imagine that the Earth and the Moon have reached the end of their story, that tidal locking was the final chapter, a permanent state of balance, a cosmic arrangement that will remain exactly as it is forever. But the truth is quieter, and in some ways even more remarkable, because the Earth and the Moon system is still evolving, slowly, patiently, almost invisibly. Even today, the Moon is moving away from us. Not dramatically, not fast enough to notice from one night to the next, but steadily, year after year. On average, the Moon drifts away from Earth by about 3.8 centimeters each year, roughly the width of a human fingernail. This tiny change is not a guess. It is measured with extraordinary precision. During the Apollo missions, astronauts placed laser reflectors on the surface of the Moon, small arrays of mirrors designed to reflect light directly back toward its source. From observatories on Earth, scientists fire powerful laser pulses toward those reflectors. The light travels across space, touches the mirror, and returns. By measuring the time that light takes to complete the journey, scientists can determine the distance to the Moon with astonishing accuracy, within millimeters. And those measurements reveal something subtle. Year after year, the Moon is getting farther away. The reason lies in the same tidal forces that once slowed the Moon's rotation. But today, the process works in a slightly different direction. Earlier in our story, tidal friction inside the Moon acted as a brake. Its rotation gradually slowed until it matched its orbit. But now, most tidal friction happens inside Earth. The Moon's gravity pulls strongly on Earth's oceans. Water rises. Great tidal bulges form. One bulge facing the Moon, another on the opposite side of the planet. If Earth did not rotate,
those bulges would remain perfectly aligned with the Moon. But Earth does rotate, and it rotates faster than the Moon moves through its orbit. Earth spins once every 24 hours. The Moon takes 27.3 days to circle the planet. Because Earth spins so quickly, the tidal bulges are carried slightly ahead of the Moon, pulled forward by Earth's rotation. That small shift changes the entire interaction, because those bulges contain mass, and mass produces gravity. The bulges pull on the Moon, very gently but continuously. And because they sit slightly ahead of the Moon in its orbit, their pull acts like a tiny forward tug, a small push, one that adds energy to the Moon's motion. Over time, that extra energy lifts the Moon into a slightly larger orbit, which means the Moon drifts farther away, centimeter by centimeter, year by year. But energy cannot appear from nowhere. If the Moon gains energy in its orbit, that energy must come from somewhere else. It comes from Earth's rotation. As tidal friction moves water across ocean basins and along coastlines, a portion of Earth's rotational energy is slowly transferred to the Moon's orbit. Another portion becomes heat within the oceans.
The result is a tiny slowing of Earth's spin. Each century, Earth's day grows slightly longer, by about 1.7 to 2.3 milliseconds. That change is incredibly small, only a few thousandths of a second over 100 years. But across millions of years, those tiny increments accumulate. Hundreds of millions of years ago, a day on Earth may have lasted only 22 hours. In the distant future, Earth's days will continue to lengthen, slowly, patiently. All the while, the Moon will keep drifting outward, moving farther from Earth. This entire exchange follows one of the deepest principles in physics, the conservation of angular momentum. Within a closed system like Earth and the Moon, the total rotational motion must remain constant. If Earth loses a small amount of rotational energy, the Moon must gain it somewhere else. In this case, in its orbit. And so the system continues its quiet transformation. Tonight, the tides rise and fall along Earth's coasts. Water slowly climbs beaches, then retreats again. Those tides are not random. They are part of the same gravitational conversation between two worlds. Every tide carries a trace of energy. Energy moving through the oceans. Energy subtly reshaping Earth's rotation. Energy gently pushing the Moon outward into space. All of it happening so slowly that no human lifetime can truly perceive the change. From our perspective, the Moon appears perfectly stable, perfectly fixed, a silent companion hanging in the sky. Yet every year, it moves a little farther away. Every century, Earth spins a little more slowly. Every tide participates in a quiet exchange of energy between two worlds. The tidal lock remains intact. The same face still turns toward Earth. Gravity still maintains the delicate alignment formed billions of years ago. But beneath that stability lies motion, continuous, patient, unstoppable. On human timescales,
The system feels eternal. But across geological time, it is still evolving, still adjusting, still seeking balance. The Earth and the Moon are not frozen in place. They are moving together through a long and graceful journey. A journey written in gravity, in tides, in the silent transfer of energy across space. What appears unchanging tonight is part of a slow movement toward an even deeper harmony, a balance unfolding over billions of years. And the full meaning of that harmony becomes clearer when we step back even further, when we return to the beginning, to the physics that shaped the Earth and the Moon from the moment the Moon first formed. Because the lock we see today is not an accident. It is the natural result of gravity guiding two worlds toward their lowest energy state. A state of quiet stability, a balance that began billions of years ago and whose deeper story is only just beginning to unfold. If we trace the story of the Moon backward far enough, we eventually arrive at a moment when none of this existed. No quiet lunar face in the night sky, no tides rising and falling along Earth's coasts, no gentle gravitational balance between two worlds. Instead, we arrive at a time of violence, a time when the solar system itself was still young, still unfinished, still forming the planets that would later appear stable and familiar. About 4.5 billion years ago, the early Earth was a very different world. Its surface was hotter, its crust thinner, and its surroundings filled with wandering planetary fragments left over from the birth of the solar system. Among those fragments was a body roughly the size of Mars, a young protoplanet that scientists now call Theia. At some point during that chaotic era, Theia's orbit crossed the path of the early Earth, and the two worlds collided. The impact was not a simple crash. It was a planetary-scale event, an explosion of energy beyond anything humanity has ever witnessed. Rock vaporized. Entire regions of Earth's outer layers melted instantly. Shockwaves traveled through both worlds, and vast quantities of molten material were blasted outward into space. For a time, Earth was surrounded by a glowing cloud of debris, fragments of rock, vaporized minerals, molten droplets suspended in orbit. The sky above the young Earth would have looked nothing like the sky we see tonight. Instead of a calm moon rising slowly above the horizon, there would have been a vast glowing ring encircling the planet, a disk of incandescent debris slowly circling under the pull of gravity. Over time, gravity began to shape that debris. Small fragments collided, merged, and grew larger. Piece by piece, those fragments assembled into a new world, the Moon. But the newborn Moon was not the calm, grey sphere we recognize today. It was a world of heat, a world of fire. Much of its surface was covered by a global magma ocean. Molten rock stretched across enormous regions of the lunar surface, glowing faintly as it radiated heat into space. And the young Moon was spinning very rapidly. Instead of taking nearly a month to rotate once, the newborn Moon may have completed a full rotation in only a few hours. Its days passed quickly, the surface turning again and again beneath the young sun. At the same time, the Moon orbited much closer to Earth than it does today. Today, the Moon sits about 384,000 kilometers away, but shortly after its formation, the distance may have been closer to 20,000 to 30,000 kilometers. From Earth's surface, the Moon would have appeared enormous, several times larger than the full moon we see tonight. A vast, glowing world dominating the sky. Because the moon was so close, Earth's gravity pulled on it with tremendous strength, far stronger than the tidal forces we experience today. Those forces stretched the young moon, pulled it slightly out of shape, created tidal bulges in its still molten interior. And because the moon was spinning rapidly, those bulges were constantly dragged across its surface. Its interior flexed again and again, molten rock shifting slowly beneath a forming crust. Every flex created friction, and friction always converts motion into heat. That friction began draining energy from the moon's rapid spin, quietly, relentlessly. Each rotation lost a tiny fraction of its energy, a small amount at first, then more, then more. Over immense spans of time, the moon's rotation began to slow. Its day lengthened, from hours to days, eventually to weeks. At the same time, the energy removed from the moon's spin did not disappear. It moved elsewhere in the Earth-Moon system. Some of it transferred into the moon's orbit, allowing the moon to drift gradually outward, farther and farther from Earth. The two worlds began an intricate exchange of motion, Earth pulling on the moon responding, energy flowing slowly between them. And within that exchange, the future of the system was already unfolding. Because the laws that govern gravity are patient and consistent. Whenever two bodies interact through tidal forces, they tend to evolve toward a special kind of balance. A configuration where energy loss becomes minimal, where motion settles into a stable rhythm. For the Earth and the Moon, that rhythm was synchronous rotation, the state we now call tidal locking. Even in the earliest moments of the Moon's existence, the conditions that would eventually lead to tidal locking were already present. The Moon was close enough, Earth's gravity was strong enough, and the young Moon's rapid spin provided abundant energy for tidal friction to drain away. Slowly, inevitably, the system began moving toward alignment, toward the moment when the Moon's rotation would match its orbit, toward the quiet stillness we see tonight. What began as chaos, fire, collision, molten rock thrown into space, gradually transformed into order, a steady orbit, a synchronized rotation, a calm companion world drifting through the darkness beside Earth. When we look at the Moon now, hanging peacefully above the horizon, it is almost impossible to imagine that violent beginning. Nothing about its silent face suggests such an origin. Yet the path from chaos to harmony was written into the physics of the system from the very start, from the moment the Moon first formed, from that instant of planetary collision. The journey towards synchrony had already begun. Not by chance, not by coincidence, but by the same physical laws that guide every orbit in the universe. And those laws are simple, yet relentless. They act slowly, but they never stop. To understand how those laws transformed rapid spin into perfect alignment, we must now look more closely at the physics itself, the quiet mathematics of gravity, and the steady forces that shape the motion of worlds. To understand why the Moon eventually became locked to Earth, we must return to the quiet physics working beneath the surface of the system. Not dramatic forces, not sudden changes, but slow, persistent interactions between gravity and matter. Interactions that continued for hundreds of millions of years.
Earlier, we spoke about tidal bulges, the slight stretching that gravity produces when one body pulls on another. Earth's gravity pulls more strongly on the near side of the Moon than on the far side. This difference in gravitational force stretches the Moon slightly, just enough to create two subtle bulges, one facing Earth, one facing away. If the Moon were not rotating, those bulges would remain perfectly aligned with Earth. But the young Moon was spinning quickly, far faster than its orbital motion around Earth. Because of that rapid spin, the tidal bulges did not remain directly pointed toward Earth. Instead, they were carried slightly ahead of the Earth-Moon line, dragged forward by the Moon's rotation. That small shift created a powerful consequence, because those bulges contain mass, and mass produces gravity. Earth's gravity pulled on those displaced bulges, trying to bring them back into alignment. But because the Moon was rotating, the bulges continued to move ahead. This constant misalignment produced torque, a twisting force, one that acted against the Moon's spin. Very slowly, that torque began to reduce the Moon's rotational speed. Not suddenly, not dramatically, but steadily. Each rotation lost a tiny amount of energy that did not simply vanish. Instead, it was converted into other forms. Inside the Moon, its interior layers flexed under the repeated gravitational stretching. Rock shifted, molten material moved slowly beneath the crust. Those movements created internal friction, and friction always produces heat. Minute amounts of heat were generated inside the Moon.
Tiny releases of energy spread throughout its interior. The total amount of energy involved was not small. In the early history of the Earth-Moon system, scientists estimate that tidal dissipation inside the Moon may have reached tens to hundreds of gigawatts. That energy came directly from the Moon's rotation. Each tiny loss slowed the spin a little further. If we were able to measure the change as a physical distance, it would be comparable to the Moon's surface rotation slowing by the equivalent of centimeters per year in angular motion. So small that no observer could detect it from one generation to the next. Yet, over millions of years, those tiny changes accumulated, rotation after rotation, century after century. The Moon's spin continued to slow. But, as before, the energy lost from the Moon's rotation did not disappear. The Earth-Moon system obeys one of the deepest laws of physics, the conservation of angular momentum. Angular momentum describes the total rotational motion of a system, and in an isolated system, that total must remain constant. If one part of the system loses rotational motion, another part must gain it. As the Moon's spin slowed, some of its lost energy transferred into its orbital motion. That energy gradually pushed the Moon outward into a slightly larger orbit. The Moon moved away from Earth, very slowly, but steadily. At the same time, the slowing rotation reduced the difference between the Moon's spin and its orbital motion. The two motions were gradually approaching one another. Rotation slowing, orbit continuing, both moving toward the same rhythm. Over immense spans of time, the difference became smaller. The bulges lagged less, the torque weakened, the friction decreased. The system was approaching a special point, a moment when the Moon's rotation would exactly match its orbital period. When that moment finally arrived, something remarkable happened.
The misalignment between the tidal bulges and Earth disappeared. The bulges could remain perfectly aligned with Earth at all times. And when the bulges no longer lagged behind the gravitational pull, the torque vanished. Without torque, the braking force stopped. The Moon had reached a stable equilibrium. One rotation for every orbit, 27.3 days. This condition is known as synchronous rotation, or more commonly, tidal locking. Once tidal locking occurs, the system becomes extremely stable. If the Moon were pushed slightly out of alignment, the tidal forces would immediately reappear. Torque would return, and the Moon would slowly rotate back into its locked orientation. In this way, tidal locking acts like a natural stabilizing mechanism, a configuration that gravity strongly prefers. Physicists often describe such configurations as minimum energy states. When systems lose energy through friction or radiation, they tend to settle into arrangements that require the least energy to maintain. For two orbiting bodies interacting through tides, synchronous rotation is often that final state. And that is exactly where the Moon eventually arrived. After billions of years of slow friction, after countless rotations gradually losing energy, after a long gravitational conversation between two worlds, the Moon settled into the orientation we see tonight. One hemisphere always facing Earth, one hemisphere forever turned away. From our perspective, the result appears perfectly still, a familiar face that never seems to change. Yet every moment of that stillness is the result of a long history of motion. Every tiny loss of energy, every subtle friction inside the Moon's interior, every quiet torque applied by gravity, all contributed to the balance we observe today. When the slowing finally reached equilibrium, the Moon entered its minimum energy configuration, a state that gravity naturally seeks.
Not a temporary arrangement, but the most stable orientation possible for the system. And once the Moon entered that state, it remains there for billions of years, drifting quietly through space beside Earth. But this minimum energy configuration is more than just a stopping point. It is a form of balance that nature repeatedly creates throughout the universe, a pattern that appears wherever gravity and time work together long enough. The Moon is simply one example, a nearby demonstration of a universal rule. And in the next part of our journey, we will see just how common this balance truly is. Because tidal locking does not happen only here. It happens across the cosmos, on worlds orbiting distant planets, on planets orbiting distant stars, and even in systems where two bodies lock to each other forever. A reminder that the quiet harmony between Earth and the Moon is not unique. It is part of a deeper pattern written into the structure of the universe itself. Even now, billions of years after the Moon first settled into synchronous rotation, the Earth-Moon system is still changing. Very slowly. So slowly that the transformation is almost impossible to feel within a human lifetime. Yet the evidence is everywhere, hidden in measurements, in ancient rocks, in the quiet rise and fall of the tides. Earlier, we saw that the Moon continues to drift away from Earth, about 3.8 centimeters each year, a distance small enough to fit on the tip of a finger, yet large enough to be measured with remarkable precision. The proof comes from instruments placed on the Moon during the Apollo missions.
small laser reflectors left on the lunar surface by astronauts. These mirrors return pulses of laser light sent from Earth. By measuring the time it takes for the light to travel to the Moon and back, scientists can determine the Earth-Moon distance with extraordinary accuracy, within millimeters.
And those measurements show a consistent result, year after year. The Moon is slowly receding. At the same time, something else is happening on Earth. Earth's rotation is gradually slowing. Each century, the length of a day increases by about 1.7 to 2.3 milliseconds. The change is almost unimaginably small, a fraction of a second spread across 100 years. But over geological time, those fractions accumulate. Millions of years ago, a day on Earth was shorter. Hundreds of millions of years ago, Earth may have rotated quickly enough for a day to last around 22 hours. The reason for this change lies in the same tidal interaction that once slowed the Moon's rotation. The gravitational pull of the Moon raises tidal bulges in Earth's oceans. But because Earth spins faster than the Moon orbits, those bulges are carried slightly ahead of the Moon. That forward shift creates a gentle gravitational pull on the Moon, a tiny acceleration that transfers energy from Earth's rotation into the Moon's orbit. The Moon gains orbital energy. Its orbit grows slightly larger, and Earth loses a small amount of rotational speed. This exchange follows a fundamental rule of physics: the conservation of angular momentum. Within the Earth-Moon system, the total rotational motion must remain constant. Energy may shift between rotation and orbit, but it cannot disappear. And so, the system continues its slow evolution, a steady transfer of motion between two worlds. But if we extend our imagination far into the future, something even more remarkable appears: a possible end state of the Earth-Moon relationship. If tidal interactions continue long enough, the system may eventually reach a new equilibrium, one in which both worlds become tidally locked to each other. In that distant future, Earth's rotation would slow until one day on Earth lasted exactly as long as the Moon's orbital period. Earth would show the same hemisphere to the Moon at all times, and the Moon would continue showing the same hemisphere to Earth. The two worlds would face each other permanently, locked together in mutual synchrony. This future state is known as mutual tidal locking, a configuration that already exists in some systems within our solar system. For example, the dwarf planet Pluto and its moon Charon are locked in this way, each always presenting the same face to the other. For Earth and the Moon, reaching that state would take an immense amount of time, perhaps 50 billion years or more, far longer than the current age of the universe. And in reality, the Sun will evolve into a red giant long before that moment could arrive, which means the Earth-Moon system will never fully reach that final configuration. But even without reaching that distant endpoint, the Moon has already played a profound role in shaping Earth's history. One of the most important effects of the Moon is its influence on Earth's axial tilt. Earth is tilted about 23.5 degrees relative to its orbit around the Sun. That tilt is responsible for the seasons. Without the stabilizing gravitational influence of the Moon, Earth's tilt might have wandered dramatically over time. Planetary simulations suggest that without the Moon, Earth's axis could shift chaotically, perhaps tilting far more steeply or nearly upright.
Such changes could produce extreme climate swings across geological time, conditions far less stable for life. But the presence of the moon acts like a stabilizing weight. Its gravitational pull helps keep Earth's tilt relatively steady, allowing the seasons to remain predictable over millions of years. The moon also shapes the rhythm of Earth's oceans, the tides. Twice each day, water across the planet rises and falls under the moon's gravitational influence. These tidal cycles stir coastal waters, move nutrients,
create shifting environments along shorelines. Some scientists believe that early tidal zones may have played a role in the emergence of life. Pools of water repeatedly filled and emptied, minerals concentrated, organic molecules cycling through wet and dry conditions. The tides themselves are part of the same gravitational interaction that continues to exchange energy between Earth and the Moon. The same interaction that slowly lengthens Earth's days and slowly pushes the Moon outward. Evidence of these ancient tides can even be found in the geological record. Certain layers of sedimentary rock preserve tidal rhythms from hundreds of millions of years ago. Patterns of ancient tides frozen into stone. Those records reveal that the number of days in a year used to be larger because days themselves were shorter. Earth spun faster and the Moon orbited closer. The rocks confirm what physics predicts. The Earth-Moon system has been evolving continuously since its formation. Tonight, when we watch the Moon rise above the horizon, we are seeing the result of this long exchange. The calm face of a world whose motion has been shaped by billions of years of gravitational interaction. The gentle tides moving across Earth's oceans, the steady tilt of our planet, the slow rhythm of days and nights, all connected to the same ancient process. What began with a violent collision between two worlds has become something very different. A quiet partnership, a stable relationship that has helped shape the environment in which life on Earth developed. The Moon's unchanging face is not a sign of stillness. It is the visible result of motion refined over unimaginable spans of time. Energy exchanged, rotation slowed, orbits widened, balance achieved. What began in violence has become the foundation of calm. The unchanging face is not the end of motion. It is motion perfected. And within that perfection lies an even deeper truth.
A truth about gravity, about time, and about the quiet ways the universe brings order from chaos. To see that truth clearly, we only need to look up once more at the Moon itself, hanging silently in the night sky. When we look at the Moon tonight, it seems almost perfectly still. The same craters, the same dark plains, the same pale face that generations before us have watched rising slowly above the horizon. For thousands of years, people believed the Moon simply did not turn, a fixed sphere, a silent companion that always faced Earth in the same way. But now we know something far more beautiful. The Moon does turn. It is rotating continuously. It simply rotates at exactly the same rate that it orbits Earth. One rotation for every orbit, 27.3 days. Because of that perfect timing, the same hemisphere always faces our planet. Not because the Moon is frozen, but because its motion is perfectly synchronized. Every step of its orbit is matched by a turn of its body. Every gradual movement through space is accompanied by an equal rotation.
the Moon is not still. It is participating in one of the most delicate dances in the solar system, a dance choreographed entirely by gravity, a dance that has taken 4.5 billion years to reach its present form. The violence of its birth, the molten surface of its youth, the rapid spinning world it once was, all slowly transformed. Spin reduced by friction, energy exchanged between rotation and orbit, alignment achieved. And once that alignment formed, it remained stable, elegant, quiet. Tonight, when we look at the Moon, the reason its face appears unchanged is simple. Every rotation it makes is perfectly matched to its journey around Earth. As the Moon travels through space, it turns just enough to keep that same familiar hemisphere facing us. No more, no less. The craters we recognize, the mountains along the lunar horizon,
the shadowed plains that shape the familiar lunar patterns, all remain visible because the Moon is turning exactly as much as it needs to. This is not the absence of motion. It is motion refined to its most perfect balance. From violent collision, to rapid spin, to slow gravitational braking, to permanent tidal lock, to the gentle outward drift that continues today. The entire history of the Earth-Moon system leads to this quiet arrangement, a state where motion and stability exist together. The Moon continues to orbit, continues to rotate, continues to move outward centimeter by centimeter. Yet the face we see remains the same. What appears to us as stillness is actually harmony. A balance maintained by gravity, a balance refined across billions of years. The face we have always known is not simply the surface of another world. It is the visible expression of an invisible order. An order written into the laws of motion, into the conservation of energy, into the patient influence of gravity acting across unimaginable time. In this quiet alignment, gravity has written one of the most beautiful equations in the solar system. An equation still being solved, one gentle centimeter at a time. And so the story returns to where it began, to the night sky above us, to the Moon. A world that appears calm, unchanging, almost timeless as it hangs above the horizon. Yet now we know that the stillness we see is not truly stillness at all. The Moon is moving, turning, orbiting, balancing itself perfectly within the gentle pull of gravity. One rotation for every orbit. A quiet synchrony maintained across billions of years. From its violent birth in a planetary collision, to its fiery youth spinning rapidly through space, to the slow breaking of tidal forces, to the graceful balance it holds today. The Moon's familiar face is the result of that entire journey. A journey written not in sudden events, but in patient change. In invisible forces, in the quiet persistence of gravity acting across deep time. Tonight, when the Moon rises wherever you are in the world, that same story is still unfolding. The Moon continues to drift slowly outward. Earth's rotation continues to slow by tiny fractions. The tides continue their steady rhythm along every ocean shore. All part of the same ancient interaction between two worlds. A silent exchange of energy that began billions of years ago and continues even now. And when we look up, we see only the surface of that relationship. The same familiar craters, the same gentle shadows, the same steady gaze that the moon has turned toward Earth for almost all of human history. But behind that quiet face lies a deeper truth, a reminder that even the most stable things in the universe are part of long evolving stories. Stories of motion, of balance, of gravity slowly guiding worlds toward harmony. There is something comforting in that thought. The idea that the universe does not rush, that it allows time for balance to emerge, for chaos to settle into order, for violent beginnings to transform into quiet stability. And the moon is one of the clearest examples of that transformation. A reminder that beauty in the cosmos often appears in the form of balance, in the steady rhythm of orbits, in the patient exchange of motion between worlds. So the next time you step outside on a clear night and notice the moon in the sky, you might see it a little differently. Not as a frozen object hanging in space, but as a world moving in perfect coordination with ours. A companion shaped by gravity, turning slowly, orbiting steadily, keeping the same face toward Earth with remarkable precision. A quiet dance that has continued for billions of years and will continue long after we are gone. If you enjoyed taking this calm journey through the physics and history of the moon,
Feel free to leave a like or share the video with someone who enjoys quiet explorations of the universe. And if you would like to see more slow, thoughtful stories about space and the hidden forces shaping it, you are always welcome to subscribe and return. I would also love to know something simple. Where in the world are you watching the moon from tonight? Somewhere under the same sky, somewhere beneath the same slowly turning companion world. No matter where you are, the moon rising above your horizon is the same moon seen by every other observer on Earth. The same familiar face, the same quiet motion, the same silent harmony. Thank you for spending this time exploring it. And wherever you are tonight, may the calm light of the moon remind you how much quiet order exists in the universe around us. Sleep well beneath the sky and beneath the moon that never stops moving.